Hello students, hope you are all fine at your homes. So let us start with the new chapter of class 9th, that is gravitation. So in this term is very much familiar to you. In your lower classes you have uh, experienced this term as a gravitational force, right? In chapters 8 and 9, that is in the last two chapters of class 9th, we have learned about the motion of different objects, and when the force is applied, then we can change the type of motion. That means the force is the cause of motion that we have learned. Also, we have learned that a force is required to change the speed or the direction of motion of an object, right? So we always observe that an object, it is dropped from a particular height. If an object is dropped from a particular height, like this, from a particular height, suppose this is a ground situation, ground place where you are standing, and from a particular height, you're having a ball and it is falling down. If you are leaving this ball, if you are making this ball fall, and it will fall towards the earth, this we know. And we know why it happens, because Newton has given a concept of gravitational force. This is falling towards the earth because of gravitational force. This we know, this we have studied. This is gravitational force. Okay. Also, we know the concept that the planets go around the sun. Planets move around the sun. Suppose this is the sun, and planets are moving in a orbit around the sun, or moon is moving around the earth. Okay, so in all these cases there must be some force acting on the objects and the planets or the moon, that we can say. So what is that force? That is a gravitational force itself. In this case also, any object is falling, there is a gravitational force, and in this case also, when the planets are moving around or the satellites are moving around, that is also because of the gravitational force. So what type of gravitational force into detail we will study in this chapter. So there are two questions coming over here. The two questions are from this concept and from this concept. The first question is, when any object is falling towards the earth, why not earth fall towards that object? Why can't we see the earth is moving towards this object? Okay, this may be the question comes into the mind. This was the question that was the answer was found by Newton and other scientists also. And this is because when we this question comes because when we are considering the third law of motion, right? So according to third law of motion, if there is a force in this direction, there must be some force in this direction also, right? But according to second law of motion, if for the given force, acceleration is inversely proportional to the mass of an object, that is F is equals to ma. Acceleration is F upon a, that means acceleration is inversely proportional to the mass of an object. Okay, so if the mass of an object is negligibly small, very very small as compared to the earth mass, then what happens, the acceleration produced will be very very large. Okay, so if the mass of the earth is very very large, then acceleration produced will be very very small according to that force. Okay, so here we can say that for a very small object like a ball, and as compared to the size of the earth, if we are comparing the two sizes, then for this the mass of the ball is very very small, so the acceleration produced in that case is large because the force is same. Okay, force is the gravitational force between these two objects, right? So for the case of ball, the acceleration produced is large, and for the case of earth, the mass is very very large, many thousand kgs. So the acceleration produced in that case will be very 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 small, because the force is same. Okay, so because these two are inversely proportional, we see that acceleration produced in the earth is very very small, that is negligible, that is, can't be noticed. Okay, so that is why we do not see the earth moving towards the ball, we always see the ball moving towards the earth. Okay, so here is the comparison of the masses, and according to the masses comparison, we can say, we can answer this type of question, that if an object is moving toward the earth, why don't earth move towards the object? So this is the answer. Okay, another type of the question that comes into mind according to this level of class 9th is that when the moon is moving in an orbit uh, around the earth, you can say, then, or we can take the example of any other planet, so around planet moving around the sun, that in that concept, why don't this moon fall towards the earth like this ball? This may be the question that comes into mind. So in a circular orbit, when it first started in the circular orbit, the circular motion concept comes into picture. Okay, what was the concept that we have studied in chapter 8? In chapter motion, in chapter 8 we have studied uniform circular motion, you remember, uniform circular motion. So in that concept of circular motion, we have seen one activity, if you remember, activity that a person is holding a thread, and with the thread, a person is holding a thread, and with the thread a stone is tied on, and when he or she is moving it in circular manner, then it will be like this, like merry-go-round. Okay, so it will be moving in a circular motion until the person is holding that thread. Okay, so in that circular motion concept, the similar concept comes into picture over here. So there is a force which is driving this circular motion. So what is that force? That force is producing some acceleration, it is changing the velocity at each and every time, because it is circular motion, and when it is changing the velocity, that means there must be some acceleration. So continuous acceleration is there in this case, and there is a force which is driving this towards the center. Okay, center seeking, driving this object into a circular path only. Why don't another path, into a circular path only? So what is that force? That force is acting towards the center, we can say. That force is acting towards the center, so there must be some force, because thread is straight when we are moving it. Okay, so we are applying that force, to the thread, and there must be some force exerted by the stone also, according to the third law of motion. Okay, that we can see. So between these two objects there must be some force which is acting as a centripetal force, that means center seeking force. That force is known as centripetal force. So that force which is driving the object into a circular path is known as centripetal force, and this force always acts towards the center, towards the center along the radius, you can say, along the radius of that circular path. And this is the force responsible for the acceleration also, that means for the changing the velocity at each and every point, for changing the direction, you can say. Okay, so if this force is not there, what will happen? If this force, centripetal force toward the center, is not there, that means in a common language, if I say that the person is leaving the thread, it is not he or she is not applying the force on the thread now, that means he leaves the thread, or maybe the thread is broken, you can say. तो अगर आप यहाँ पे छोड़ देंगे उस thread को, so what will happen? The stone will move away and it will fall somewhere away from this circular path, okay, away from you. So at the point where you are leaving the thread, the force, this force makes this object move in a different direction and not in the circular direction, because that force, and with because in that case the object is must be having some velocity. Okay, so if the velocity is higher, then it will move further. And in which direction it will move? It will move in the direction of the tangent to this circular path. Now what is tangent? This I have explained in your chapter 8 also in this topic. So the tangent is perpendicular to the radius at a one point for a circle, and this one point is only this tangent is touching, this line is touching only at the one point on the circle. Okay, so in this direction, if the object is moving like this, so in this direction the object will move, and with a straight, on a straight path, on this straight tangent line, the object will move and go away from this circular path. So that's what will happen. Newton said that that's what will happen to the our planets also, that may happen with the moon also. If this gravitational force is not there between earth and the moon in this line, and then it must go away at the in the direction of this tangent. If it is moving like this, so it will move away and go with the uniform velocity with the in the direction of the tangent. Okay, so this was given a point that at each point of its orbit, at each point of the orbit in a circular path or an elliptical path, the moon tries to fall towards the earth instead of going on a straight line, because it is attracted by the earth at every time. Okay, at each and every time it is attracted by the earth, but we do not really see the moon falling towards the earth. It is not falling towards the earth because of this centripetal force, which is making it move in the circular manner. So here, after this, Newton generalized this idea, this complete idea. He generalized and he came to the conclusion that it is not only the earth, which attracts the other objects. Rather, there exists a force of attraction between any two objects in this universe. Any two objects, whether these are small objects or these are very large objects, or these may be planets, these may be a ball and a earth, these may be you and me, these may be one pen and this cap. Okay, so any two objects in this universe, there must be some force which is existing between these two objects, and that force he called it as a gravitational force, and that the name of that force is a gravitational force. So here in this section, in this chapter, the idea of gravitational force is different from here. Okay, why? Because till now we have understood that the gravitational force is only the force of attraction of earth. In the lower classes we studied this. Okay, but now the Newton has explained it in a different manner, and that we are studying, and that different manner is the generalized idea, which can be which could be explaining that there is a force of attraction between any two objects in this universe. So for that he has given a law that is known as the universal law of gravitation. Okay, so that gravitational force is not only for earth or for any other planet or for moon. Okay, it is now for every object in this universe, not this world, in this universe. So that idea has been combined into a law which is known as the universal law of gravitation. What it is? Universal law of gravitation. So according to universal law of gravitation, there exists some force which is known as force of gravitation or gravitational force between any two objects in this universe, right? So this we will explain. I will explain you this universal law right now. So now this universal law of gravitation. This law states that the force between any two objects is directly proportional to the masses of those objects and inversely proportional to the square of the distance between between those two objects. So let us consider, for understanding this, let us consider the two objects. These two objects can be two balls, these two objects can be two planets also. So let us name these two objects as object A and object B. For understanding, I am taking these as object A and object B because in your book it is similar denotation it is given in the NCERT book. Okay, so let us say these are two large heavenly bodies like two planets maybe, or a earth and a moon or anything. Okay, so why I am saying this, because for heavenly objects we have to consider the distance between the center point of that spherical object and the surface. If it is earth, okay, so earth surface is this one and earth center is this one, so there is a large difference between the distance. Okay, so that is important to consider that distance. This is not negligible. But if it is a ball, a small ball, then this radius of that ball is not very large distance, it's very small distance, so it is negligible in the concept. But we have to take a generalized concept, so we will consider this and this radius, and later on for a small object we can neglect that radius from that formula. Okay, so I will consider this as a heavenly objects and consider this radius also, it is not negligible over here. So these are two objects A and B, and let us say the masses of these objects are m1 and m2. m1 and m2. So mass of first object is m1 and mass of second object is m2. Let us say the distance between these two objects. What is the distance between these two objects? The distance should be taken from the center point. Okay, so what is the center point? This is the center of these two objects. So that is why I was saying in the beginning that it should be considered. Okay, this distance should be considered. So complete distance between the two objects will be measured always from center to center. Okay, so this distance is small d. Let us consider this distance as small d. So what will happen if I don't consider this radius? So if radius of the earth or any other planet is so many kilometers, so the distance, this much distance, surface to surface distance should not be considered, this should be considered. Okay, so from center to center we always take the distance in this case. Okay, so now what does this universal law says? That the force between these two objects. So what is the force of attraction? Force of attraction between, universal law of gravitation says that the force of attraction between these two objects, attractive force is always shown by these two arrows towards each other. Okay, gravitational force is always an attractive force, it is not a repulsive force. Okay, it's always an attractive force. So attractive force between these two objects will be F. Let us say this is F. Okay, so this force between any two objects in this universe is directly proportional to the masses of these two objects and inversely proportional to the square of the distance between these two objects. Okay, so mathematically I can write down as force directly proportional to the product of the masses m1 and m2, and it is also inversely proportional, means 1 upon distance, inversely proportional to the square of the distance, that is d square. Okay, so it is inversely proportional to the square of the distance between these two objects, right? So this is the universal law of gravitation. And mathematically, if I want to find out the formula combining these two concepts, then, or you can say these two equations, from equation 1 and 2, mathematically I can write down by combining these two equations, combining equation 1 and equation 2. F is directly proportional to m1 m2 divided by d square. Okay, so this is the mathematical expression, right? Now here inversely or directly proportional, that means proportionality sign is there. If I want to find out a particular formula or derive a relation, then I have to remove this proportionality factor. And how to remove, that we have done in the last chapter also, chapter 9, while deriving f is equals to ma, right? You remember f is directly proportional to ma, and we have found f is equals to ma by using a constant of proportionality. So here also constant of proportionality I will consider. F is equals to constant of proportionality, here I will consider as capital G, and that is having a particular value, very very important value. So capital G is constant of proportionality over here, and the formula becomes m1 m2 by d square. Other things remain the same. So I will multiply by a constant of proportionality in this case. So what is the formula of force of gravitation? This becomes the formula for force of gravitation, where G is the universal gravitational constant. Universal gravitational constant. Okay, now what is the value? What is the value of this universal gravitational constant? Earlier in F equals to ma, the k was the gravitational constant of proportionality. So in that case the k was 1. So here it is not 1, here it has a particular value, and that value is given by the experimental concepts, and this value is 6.67 multiplied by 10 raised to power minus 11 Newton meter square per kg square. This is the value of universal gravitational constant. It is very 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 important concept and very very important formula. Okay, so here how will I define this universal gravitational constant? Here I can define universal gravitational constant also, and I can find out this also from this formula. So how will I define universal gravitational constant? So to define this, we will use this formula only. So I will just turn over the page. Let me take this. F is equals to, I am writing it again, G m1 m2 divided by d square. So from this formula I can define the value of G. If the force between the two objects m1 and m2 objects A and B we have taken is will be equal to gravitational constant if the objects are having masses 1 kg and this is also 1 kg and the distance between those two objects is 1 meter. Okay, if this is 1, this is 1, this is 1, then what the equation becomes? Equation becomes F equals to G. So what is universal gravitational constant? That is equal to the force of gravitation. So how this is how we can define, that is universal gravitational constant is defined as the force between the two objects of unit mass, that means 1 kg mass when each are separated by a unit distance from each other. Okay, this is how we can define capital G. So how did we get the SI unit of capital G? SI unit of capital G, that was Newton meter square per kg square. This SI unit we got from this formula itself. Okay, so because of this formula I can write down G is equals to FD square divided by M1 M2, right? This I can write down. So from here this is force is having SI unit as Newton, D that means meter, and it is D square, so meter square divided by kg and kg, so kg square, so Newton meter square per kg square. That is what I have written for the SI unit. This is how we can find out. So the value of G, that is I'm writing again 6.67 multiplied by 10 raised to power minus 11 Newton meter square per kg square is given by a famous scientist named Henry Cavendish. DISH, Cavendish. Henry Cavendish gave this value. Okay. So this universal law has many important facts related to it. That means it will what is the importance that is that it gives us the force, it tells us about the force that binds us to the earth, force of gravitation that we have studied, and it gives the relation of the motion of moon around the earth, it gives the motion of other planets around the sun, it tides due to the motion and the sun, the tides due to the motion and the sun that are created, that the reason for that also it is creating. Okay, hope you understood this topic very well. Thank you so much.